So I'm René. I'm at NVIDIA in Zurich. Before that, I was a researcher. I did research in London, in the US, working in hardware acceleration, that includes FPGAs, and now, obviously, GPUs. So I'm really excited to talk to you about RAPIDS today. RAPIDS is a platform, if you wish, contains a set of libraries that you can use for traditional machine learning, traditional hearing sense, everything that's not deep learning, and analytics. Well, traditional sense and analytics. And if there's one thing that you should take away from this talk is, if you know Python, you use pandas, and you use scikit-learn, then you can or you should try RAPIDS. We'll try. So, one of the data scientists around here, we are facing a couple of challenges. And challenges in our daily work is we have to deal with lots of data. Now we have an onslaught of data coming in. Data comes in very different shapes and forms, and we have to somehow ingest it in the system. The second problem is the problem we want to talk about today, which is really the compute problem. You don't only have to ingest the data, you have to actually process it. And data science, what you do nowadays on your laptop, really is a HPC, a high performance computing problem. Right? So you can only throw as many CPUs at this problem. CPUs are not getting much faster these days, so you're going to have to rethink how you can really handle that increased compute demand. And then finally, the data science software stack is very heterogeneous in the sense that it's usually just a plumbing of different components of more or less lower and higher quality plumbed together, and you have to do it in a deployment fashion. You have to take care of the DevOps situation, right? It's the whole software maintenance. So I want to talk a little bit about the compute side of things, where we have some solutions. So those of you who've used TensorFlow or PyTorch, you have probably used, as part of your setup, you've probably used cuDNN, which is a deep learning acceleration library, and it's built on top of CUDA. CUDA is our compute stack that allows you to program GPUs similar as you would a traditional CPU. It's a C++ programming language in the platform. So within that context of accelerated libraries, we call this CUDA-X, X stands for acceleration. We have a bunch of libraries in that space next to cuDNN, cuBLAS, for linear algebra. We have a group of new libraries for data processing. It's the traditional pandas-like data processing, which we call DF. DF stands for data frame. And then machine learning, QML, that goes to methods that are not here in that deep learning space. And then there's also cuGraph for graph analytics that has become more important these days. So these are libraries. These are open source libraries, so you find those on GitHub. You can compile them, then you have SO files, and you can include them in your own application if you want. Or, probably more likely, you're going to use them integrated in some framework, in some platform. One of these platforms is RAPIDS, which is essentially just a Python binding of these libraries. And then you're free to deploy them whenever you want. You can deploy them in your as a Python notebook, or you can have your complete Kubernetes pipeline run in that. Finally, then the question is then where do you run it? Well, you can run it on your laptop or your data science workstation, or if you need more power, you can go and get one of these servers that we have, one of them downstairs at the exhibition, or you can decide, well, I don't want to deal with hardware myself. You can use somebody else's hardware and deploy it to the cloud. But the key here is that this is one single platform with one single acceleration library that was written by us, making sure that we're getting the most performance out of the hardware platform, wherever that hardware runs. So where does this come into picture? You have heard this morning, very nice talk by someone from Tableau, is really the explaining one phase of the data science workflow, which is the exploratory phase. right? That's the kind of phase that we want to focus here for today. Let's assume you get the data somewhere in the system, and the data scientist starts doing some exploratory analysis of the data, figuring out what cardinalities are present, where correlations, maybe some histograms, view visualization comes in the picture. And then you're taking a sample of the data, training a model, playing around with the model, evaluate the model, and then we end up with some sort of a recipe model, which is then fed to the data engineer who throws the big data at the problem, right? So and you also, this is the one who has the big iron machine that actually cranked through the data. You get the model, maybe you want to deploy it in the field, and then usually, as it happens, we might find that the model might not satisfy our needs, so we have to go back, and so we have this iterative process. Now, if we zoom in on that part, just the model building or the exploratory part, which is really interactive, we find that loop again. So we start with the sample data, do some data exploration, do feature engineering, training, scoring, and then you have to go back. Usually multiple times, and you don't want to leave the training running overnight. You want to have this interactive. We had the same issue before with regular business intelligence, business analytics, where we just had to wait for the data until the report actually completed. That give rise into those systems like HANA or DB2 Blue. So now, what's the setup here? So what I'm going to show you today is two parts. We're going to talk about the data analytics part through QDF. You can call this the data preparation, and then the machine learning part, QML. The data preparation is really operating these days on the concept of a data frame. I don't think I've explained in this audience. It's what we provide here is a pandas-like acceleration, a pandas-like GPU accelerated version of pandas, so to speak, that is built in CUDA. There's also development currently going on in Spark, for Spark, to do the same thing in the Spark ecosystem. We haven't made any announcement really about that, but everything is sort of out in the public, so if you want to figure out where to stay in that project, it's just look at the Spark JIRAs, and then you can find the state of that project. And then the next step is the actual machine learning is QML, and here the model that we're trying to get people to use from is the scikit-learn like interface. So people are familiar with scikit-learn, and they want to switch over to a GPU-optimized implementation of the same algorithms. And beside that, there's also XGBoost. We have a team that has worked on GPU optimization of XGBoost. XGBoost, so to speak, is not part of RAPIDS, but we offer an interface that, for example, we can easily extract a GPU data frame into a GPU matrix for XGBoost. So I thought I'll start with a simple example. And the contrast pandas and QDF, on CUDA GPU data frame. Pandas is really your modern style spreadsheet. It's a table, and every column has a different type. The way it's laid out in memory typically is either NumPy arrays that are stored somewhere in your host memory. And now we do the same thing here with GPU data frame, which is semantically the same thing, so for the user it looks the same, but it resides in GPU memory. And in GPU memory we have GPUs of up to 48 gigabytes per device. We can put 16 of those together, and then we end up with like 512 gigabyte large systems of device memory. So we can fit a lot of data already in your device. And then you can operate out of the device at a bandwidth of 600 or more gigabytes per second. The representation here is based on Apache Arrow. Who has heard of Apache Arrow? There's a number of people. This is an interchange format to enable interoperability between different operating systems. Essentially, it's a columnar format to make sure that we're only accessing data bringing in data from memory of those columns we're actually interested in. Right? Databases, column stores currently make use of this technology. So what I thought I will do, I will take an example, specifically the KDV COP99 dataset, and just to do some exploratory analysis. Let's do some DB clusterings and density-based clustering. And I want to show you on one side what it looks like in pandas and scikit-learn, and then the other side, what's in green, in NVIDIA green, what's on the GPU, right? What's in QDF and in QML. So the data set is an intrusion detection challenge. It was a very old data set where we have each row is a connection, essentially, connection network link, and the challenge is to build a classifier to distinguish, for an intrusion detection system, to distinguish good traffic and suspicious traffic. So this is the data set, and we're going to do some clustering to figure out how many clusters. Maybe we can do some anomaly detection, maybe by figuring out if we have outliers from the common pattern, that these might be potential bad guys. So I have this. I didn't have the setup here to run this interactively. I think I have to upload the PDF, but I uploaded 2 Jupyter notebooks to this talk. You shouldn't talk in this talk app. You should be able to download them, and then you can run them yourself. We also have a booth downstairs, so if you're interested, come to me and we can do this real. But for now, let's just focus here on the PDF, on the slides here. So let's bring in the data first. Pandas is, we import pandas into pandas read, gives you the PDF here. PDF, I use the name PDF to differentiate it from the GPU data frame. Like the PDF is a pandas data frame, whereas the GDF is a GPU data frame. And then you check how many rows there are. You can get you get the schema of the data frame. So we do schema inference the same way as pandas does the schema inference. So here the point is that there's really not much difference. There's almost virtually no difference between the APIs. So if you're familiar with one, you could use the other. And the next thing maybe you want to do is you may want to have some expressions. So here's an example. You can have a columnar expression with an assignment. Create a new column that has the sum of the traffic. The total traffic is the sum of traffic going this way and traffic going that way. You can have predicates. Here is a concept of a Boolean indexing. So you have a predicate on the column with a literal that gives you then a binary vector, and then you can use this to refer to as the index. You can look up the corresponding column, and then you get some initial statistics about the data. You could also do joins. Here maybe an example where you want to, so this, the column has a service, the type has a service column, which is a string that tells it what kind of traffic it is. This is HTTP, FTP, and so on. Let's say you want to join that with some other table, and it's some other data frame that maybe has the port numbers in it. So that's a typical relational natural join that you can do. And the way you can do this, well, you specify here the traffic types I want to look at. And then here are the corresponding port numbers. And then I can do this, both the join and as well as selection, predicate selection through this dimension essentially up here. And here the command that I use is GDF merge, the same way as I would do in pandas. So the point here again, long-minded, it's the same thing. And let's say we want to focus now on port 80 and look only a subset of the columns, so we can do a column gather and apply predicates this way. So we got the number of rows down to 623,000. Next, what can we do? Well, let's do some feature massaging, some data wrangling. Maybe we should standardize it, so it's zero mean variance over here. Then you could do this way. Just iterate over columns. We also take the first 20,000 columns just to get the results fast for pandas, and convert it to a float and do the mean variance and the usual division here, standardize it. Typically, you would use the standard scaler from scikit-learn, but that's not yet available in QDF or QML. So as we currently building this up, we are still at version 0.7, so it takes a bit until we're at version 1.0. Yet we have all the features in there. And then finally can switch now to scikit-learn QML. Just import the corresponding package and run dbscan with the same parameters, the epsilon distance, and the number of samples, minimum number of samples per cluster, and then I run fit. And then you see here, that's the GPU, the CPU time in pandas using all cores, and that's the time it takes on the GPU. Then you can print the cluster output here. So one thing to notice as well, there's obviously this time difference. Using here all cores, it takes about 8 seconds, and here it takes about 0.3 seconds on one GPU. You also notice there's a difference in the results. Well, this is primarily due to the fact that you have to use different implementations of the algorithm. So what we're doing here, we're using GDP-scan, which is doing the pairwise comparison. It's also a pairwise comparison, but it actually uses builds a graph, a neighborhood graph, and then does it in parallel, and then you can do breadth first search in parallel to that. So that's this. Now you have seen here that we're only using one GPU. There's a full set of laundry list from algorithms that we currently have available, in addition to XGBoost that's there. That's outside of QML. Inside QML, this is the current list of supported algorithms. So we have some clustering algorithms, k-means, dbscan, nearest neighbor, then linear regression, some column filter, and then dimension reduction. And we also have a couple of solvers that we expose for you, that we use internally, but we expose that into the Python world. You can see here most implementations currently only support single GPUs. That means if you have a multi-GPU system, you will only be able to make use of one. The way we're going to go with this is to use Dask as the mechanism to distribute the work. So I know people are familiar with Spark. Who has heard of Dask? Also, substantial number of people. That's good. So Dask is a parallel compute platform for in the Python system, and it also supports distributed data frames using essentially horizontal partitions. So the idea is for GPU1 will get one partition, GPU2 the second, and so on. And what we currently have also in GitHub, there are two libraries that you can use for the distributed setting. So distributed means multi-GPU within a single machine, or also multi-GPU across machines. Then you can use UCX or MPI type communication, GPU RDMA to exchange data. And also here, currently the algorithms are wrappers around the single GPU versions. We trying to at some point move them back in the corresponding single QML and QDF repositories. But that's the situation how it's nowadays. And the question is, where do you run it? Well, you can run it on your laptop, on your GeForce at home. You can run it on the cloud, within a container, or there's some services that even allow you to have notebook directly as a Jupyter Hub. If you need more compute power, we can use what we call a data science station, essentially just a system with 2 quadro GPUs inside. It gets you up to 96 gigabyte device memory, so that's GPU memory. It can go up to the enterprise card, where it fits into the 75 watt power budget. You can also use it for inference. And then, of course, the bigger systems that we have, the DGX1000 for display. Right. So how do you get started? Well, there's the link up there. RAPIDS AI Get Started. and it really depends what your setup you have. So if you have a Linux laptop with a Pascal GPU or later, then you can just, on your Anaconda running, just install RAPID through this a bit lengthy install, get all packages from the right channels. Probably easier then would be you can install and run a Jupyter notebook from a Docker container. The point here is you need the NVIDIA Docker plugin to get the GPU passed through. But you can pull the container image from RAPIDS or from our Docker hub in the GPU cloud. Or what you can also do, you can run that inside cloud itself in a notebook, for example. You can use the Azure Machine Learning Service, or there's an experimental version of RAPIDS in the Google Deep Learning image. Or even probably the easiest one is a collaboratory from Google. This is one notebook I uploaded, so essentially you download that, put this on your Google Drive, you double click on it, and then you're up in the Google Collaboratory, and you can play around there with the T4 GPU. Yeah, that's what all I have. Thank you very much for your attention.